So in this question, we have a linear spring of negligible mass. So we have a force, and it causes length to increase. So immediately we should be thinking Hooke's law. So the force of the spring is kx, and we have a force, and we have a change in length. So that means we can solve for k, and k then is going to be Fs over x. And the force of the spring is 18.0 newtons, and that is over 1.0 centimeter. So that is 0.010 meters. That gives us a K of 1,800 newtons per meter, and that has two significant digits because the centimeter has two significant digits. All right, so then we have a sphere of mass 75 grams is attached to one end of the spring, so that's this over here. So this is 0.0750 kilograms. Need to convert it all. And the distance between the center of the sphere is 25 centimeters, which is 0.25 centimeters. 0.25 meters, excuse me. The sphere is rotated at constant speed in a horizontal circle with the center P. So that means that we have a center P. There's the spring, and there's the mass, and it would travel in that orbit. And so that is 0.25 meters, and this is 0.0750 kilograms. Now, the interesting thing is that once this starts to revolve, the length changes. So now the spring extends a little bit and now travels in this orbit. And that distance is, R is 0.265 meters. And so we are asked, why does the spring length increase? Well, the first thing to realize is that the spring length, 0.25, is its equilibrium length. So to start, the equilibrium length is 0.25 meters. The sphere is accelerating because its direction is continuously changing. The centripetal acceleration is caused by a centripetal force that comes from the spring. The spring applies the force that causes the change in direction and thus the centripetal acceleration. So we apply our rules here. What are the facts in the case? The equilibrium length is 0.25. That's a fact. The sphere is accelerating because its direction is continuously changing. And so that's really more of a observation. And we have a centripetal acceleration caused by a centripetal force, which is true, and the conclusion is that it comes from the spring. And then to say the whole thing over again, the spring applies the force that causes the change in direction, and thus the centripetal acceleration. So there we have our three-part situation. The next question is to determine the speed of the sphere. Well, we have acceleration, and acceleration is usually often related to Newton's second law. So we have the net force is equal to the sum of the forces. The net force is equal to the mass times its centripetal acceleration. And the force in this case is simply the force of the spring. The AC is V squared over R, and the force of the spring is Kx. And if we're looking for the V, we need to solve for V. So V squared is Kxr over M. And then V is the square root of Kxr over M. And when we divide that out, we get 9.7672 meters per second. And then we're asked, now let me put the numbers in here. So you have them to go by. The K is 1800. The X, the elongation, is 0.015. R is 0.265. And the mass is 0.0750. So the 0750 has 3 significant digits. This has 3 significant digits. The 015 has 2, and so does the 1800. We can only report 2. So the velocity is 9.8 meters per second. And that's A14.